Good morning, grade 11. Hope you are all doing fine. This is Miss Pamela Teeny giving the physics course. Today we are going to start with Chapter 5, Section 3, Forces in Two Dimensions. If you can all please open page 136 so you can follow up with me. In the previous sections and chapters that we studied, we talked about forces in one dimension. For example, Fn, Fg, friction forces. Today we are going to talk about forces in two dimensions. First of all, we are going to study equilibrium force. So what is an equilibrium force? An equilibrium force is a force which brings a body into mechanical equilibrium. So the first sentence states that if you add the equilibrium force onto a body, this body becomes in equilibrium. According to Newton's second law, a body has zero acceleration when the vector sum of all the forces acting upon it is zero. So, as we already discussed in Newton's second law, whenever a body has zero acceleration, it doesn't mean that the body has no forces acting on it at all. It means that the summation of all the forces acting on the body is zero. Therefore, an equilibrium force is equal in magnitude and opposite in direction to the resultant of all the other forces acting on a body. So, if you want to find the equilibrium force of a body, you need to add all the forces acting on the body and you get the resultant force as we studied in section 1, and the equilibrium force is equal to this resultant force in magnitude but opposite in direction. So they are parallel and equal in length but they are opposite in direction. So if the resultant force is upwards, the equilibrium force is downwards. If the resultant force is to the right, the equilibrium force is to the left. So once you find this equilibrium force, if it is added to the body, this body becomes in equilibrium. For example, find the equilibrium force of an object upon which two forces are acting. The first with a magnitude of 19 newtons to the right, and the second with a magnitude of 12 newtons upwards. In order to find the equilibrium force, first we draw the free body diagram of the object, as you can see in the figure in front of you to the left. We draw the object as a dot, and the forces are coming out of the object. The first one is 19 newtons to the left, and the second is 12 newtons upwards. Second, we find the resultant force using what we learned in section 5.1 about adding vectors. So you should remember how we used to add vectors. First, we draw the first vector, the second tail to head, and the resultant vector is drawn from the tail of the first to the head of the last. Finally, we draw the equilibrium force, which is parallel and equal to the resultant force, but in the opposite direction. So as you can see in the figure in front of you, the resultant force is upwards while the equilibrium force is downwards at an angle. So they are parallel, equal in magnitude, but opposite in direction. So in the second part of this section, we are going to talk about forces acting on an object on an inclined plane. First, we have to define an inclined plane. An inclined plane is a tilted surface. So it is a surface that has an angle with the horizontal. You have applied Newton's laws to a variety of situations, but only to motions that were either horizontal or vertical. How would you apply Newton's laws in a situation such as the one shown in the following figure, in which you want to find the net force on the box? So as you can see in the figure in front of you, the box is the system and it is on an inclined plane. Now we are going to study how to apply Newton's laws to such an object. In order to solve such a problem, first we need to identify the forces acting on the system. In this case, the box is the system. First, we have the gravitational force, which acts on the box downward, toward the center of Earth. Second, we have the normal force, which acts perpendicular to the incline. And third, we have the kinetic friction, which acts parallel to the incline and opposite to the object's motion. So if the object is going down on the incline, the friction is upwards. However, if the object is going up on the incline, the friction is downwards, opposite to the motion. Second, we need to draw the object's free body diagram. As you can see in the figure in front of you, the object is represented as a dot, and the three forces acting on the object are represented as vectors coming out of the dot. The normal force is perpendicular to the inclined plane, the gravitational force is towards the center of Earth, and the friction force is opposite to the motion of the object. Third, we need to choose the coordinate system, which is made of the x-axis and the y-axis. The x-axis should be in the direction of the object's acceleration, which is parallel to the inclined plane. However, the y-axis is perpendicular to the x-axis and thus perpendicular to the inclined plane, parallel to the normal force. As you can see in the figure in front of you, I drew the x-axis and the y-axis. The x-axis is parallel to the inclined plane, as we said, and the y-axis is perpendicular to the x-axis. As a homework, please find the equilibrium force of the objects with the following free body diagrams. The first one has two forces acting on it, 20 newtons and 15 newtons, in the directions shown in front of you. And the second has three forces acting on it, 7 newtons upwards, 25 newtons to the right, and 21 newtons in the direction shown in front of you. The second number of your homework, a girl is going down a slide that is inclined at 20 degrees above the horizontal. A. State the forces acting on the girl. B. Draw her free body diagram. And C. Which of these forces have both X and Y components? Please, your homeworks must be done by 26 March. In our next session, we are going to continue this section and we are going to explain how to calculate the forces acting on an object on an inclined plane, each force on its own. Thank you and good luck.